All right, here we are.
All right. For question three, and I believe in question five, um, so for question three, do I so we already know one like B is an odd number. Do we still need to show proof that B is actually an odd number by giving like the equation because or do we have to just we can assume like three is already like B is already an odd number, given the fact that we it should be self-explanatory.
Okay, well let's just look at the problem really carefully and read it
Okay,
together. Here we go. I'm going to share my screen with you
okay.
so that we can look at it together. All right, so problem number 3 says prove this universal statement. If A is even, can you see it okay?
Mm-hmm.
B is odd and C is even. So we've got 3 pieces to this compound hypothesis.
Okay.
It's already written as an if then, so we don't have to do that part. That's already done.
Yeah.
But we do need to use the definitions of even and odd. So on number 3,
Um,
what do you think your hypothesis should be?
for number three,
What should we assume?
oh, true. Assume A um equals
Well, why don't we just say assume A is even? Then we'll get into the definitions in a minute.
okay,
Like
assume
in the
A is even
hypothesis, you just want to say the simple stuff. A is even, B is odd, okay? And what else?
and C is even.
Exactly.
And do I have to provide examples for
Nope.
A, B, and C, or do I just have to kind of um
That's a great question. It's a universal statement. We're going to prove
okay.
that it's true for all integers. It's universal. It's an if then.
Okay.
So we assume this stuff. And what do we wish to show?
We wish to show A times B and B times C is
Minus.
sorry, minus B times C is even.
Okay. That's the way you want to set it up. Just nice and simple. You've got an even number A, an odd number B, and an even number C. And then we want to show AB minus BC is even. Now
Okay.
we dive into the definitions. So by the definitions of even and odd, what do we know? What
We
should
know that
okay?
A n that numbers A I'm sorry, A n equals 2k,
Good.
B equals 2h plus 1,
All right.
and C equals 2. Let's not use, I was gonna say B, but can we use E?
Sure.
Okay.
And we got to say the second part of the definitions. K is an integer, H is an integer, and E is an integer.
Okay.
Because these definitions all have two parts, right? They
Okay.
have information that's an equation. So we have these nice equations, but we also have information about these variables that we've introduced. We have to
Mhm.
tell the reader they're integers. Hang on, I'm going to grab my dog. He's outside barking.
Okay.
Here you go. Good boy. Good boy. Good boy. So now let's unpack this wish, okay? When we say
Okay.
we wish to show that AB minus BC is even, what are we really showing here? What do we really wish to show? We want to show that AB minus BC equals what? We got to have an equation here because we got to satisfy even here.
Let's do 2G plus 1.
Oh, but we
Oh,
want it
sorry, 2G, 2G.
good. Where we got to say something about G.
G is an integer.
Excellent. Perfect. So you're all set up. You've got these nice equations. You've got that A is equal to 2K. You've got that B is equal to 2H plus 1. And you've got that C equals 2 times E. And K is an integer, H is an integer, and E is an integer. So we've got 6 pieces of information we're going to use.
And now do we have to provide like examples like plug in for A, B, and C?
No, no, because this is not an existential statement that we're proving. We're proving a
Okay.
universal statement. And when we're proving a universal statement, we just use variables, the definitions, algebra, and then the things that we are allowed to assume, like sums and products of integers, or differences of integers or integers.
Okay. For the special homework, do I have to put it in the same format as like the first like number one, like A, B, and C, or can I just use like the whole space for number three?
You can just use yeah, the guidelines would be to write it as an if then, if it weren't already written as an if then, but it is already written as an if then. So,
Oh, okay.
right. But we're indicating where our proof begins, and we're stating our hypothesis, and we're stating our wish. And now we've used the definitions, right? And
Right.
now we're actually going to try to do what we wish to do. We want to look at AB minus BC.
Mm-hmm.
See, that's the nice thing about expounding on your wish. Like
Oh,
looking
okay.
at that wish really closely shows us, ooh, we got to look at AB minus BC, because that's what we're going to try to say something smart about. We're going to try to
Yeah.
show it looks like 2 times something. We're calling it G here,
Mm-hmm.
but it won't just be a single letter. It'll be some kind of expression that we'll be able to argue is actually an expression representing an integer.
Okay.
So, we can we can look at AB minus BC. So looking at AB minus BC, what do we see? Okay, so A times B minus B times C. We start to use substitution.
Okay.
Does that make sense?
Mm-hmm.
And then you would substitute in for A and for B, and substitute in for B and for C, and do some algebra and try to pull a 2 out.
Okay.
And you should be able to factor out a 2 from everything if you do the algebra right.
Oh, okay.
How's your algebra?
Um, I think I can give it a shot. Um,
Good.
so 2 times G is okay,
Well,
so we have
we're going to substitute in for A and B and B and C. We're going to start using our proof money at this point.
because
See, we know
A,
what A looks like, right?
yeah,
So we plug in for A. See what I
okay,
mean?
2K is A,
All right. And we're going to multiply that by B. What is B?
B is 2H plus 1.
Great. So
And
that's
then
AB. Good.
and
Minus.
then obviously we would minus that out with 2C. Sorry, 2E.
Okay, well, I'm gonna put the C last. If you, the C is here, 2E is the C, but we need B in front of that.
So 2H plus 1.
Yeah, we're gonna use that again. Good. So that's what we're looking at.
Okay.
And then if you do the algebra, and if you do that right, you should eventually pull a 2 out of everything. And then what's left here is going to be your G.
Oh, okay.
And that's what you're going to argue is an integer.
Oh, okay. So you're basically like factoring out this equation, right?
You're, you're factoring a 2 out of, right, we have this equation and we want the left side to look like it does, AB minus
Hmm.
BC, but we want to make the right side of it look like 2 times something. We're calling
Yeah,
it something G, but that is going to turn out to be a big expression because it's
true.
going to be in terms of all this stuff, you see.
Okay. All right.
And then we have to talk about why G is an integer. Well, it'll what builds G will be an expression with K in it and H in it and E in it and maybe some numbers and some pluses and minuses and things will
Okay.
be getting multiplied or subtracted or added. And so we
Hmm.
talk about why G is an integer because sums and products and differences of integers are integers. That's why G is going to turn out to be an integer because it's going to be built from integers that are getting added or multiplied or subtracted or all of those things.
Okay. All right.
Does
I
that
think I
help?
should be able to figure it out tonight.
Good,
All right.
good. Now, did you have a question about number 5?
Number 5. So same thing. Hold on, let me see.
I think I have
So
a
same.
typo. I think I have a typo. I think it's supposed to be x is equal to n squared. Is that a typo or is it equal to?
Hold on. Let
Oh
me.
yeah, no, it looks good. The
Okay, it
definition of
looks good.
perfect
Okay.
square. Yeah, I thought I had a typo.
Cause yeah, it's just like an ex universal statement.
But we're going to decide if it's true or false. If it's true, we prove it. If it's false, we try to find a counterexample, and that's when you would give actual numbers to give a counterexample. Have you looked at some examples?
I actually for like perfect squares.
Uh-huh.
Um, I did look at some perfect squares. However, the original statements thing for all of m and n being an integer, because m can't always be a perfect. All of m are not perfect squares, technically.
That's right. So the point is, if this is true, then no matter what we pick for M and N, if we pick an M and an N where their product is a perfect square, then the claim is that both M and N would be perfect squares. So let's look at some perfect squares. Like here are some perfect squares. Well, if we start listing the perfect squares, starting with the smallest one,
Which is one, obviously.
actually, 0 is a perfect square because it's equal to 0 squared. But yeah,
Oh, okay.
then, yeah, I know, right? Then 1 is 1 squared. What's the next perfect square?
Um, four
Yeah, 4
is
because that's 2 squared. Good. What's the next
exactly.
one?
Um, eight.
8's not a perfect square.
Oh, okay. So two times two is four times 2 is, oh, 3, oh, 9 actually.
Great.
I was thinking of 2 cube. That was,
Yeah, right. You're right, right, right. You got your three, you had your three and your two mixed up.
yeah, yeah.
That happens. Okay. What would be the next perfect square?
16.
Yeah, exactly. And so we have enough to go on right here because
Yeah,
we need to see m times n would need to be a perfect square. So let's look at some examples where m times n is a perfect square. And here we might want to, 1 and 0 aren't going to help us because 1 is going to be a perfect square and and 0. But it says if mn is a perfect square, then the claim is that m is a perfect square and n is a perfect square, right? That's the conclusion is a compound conclusion. It's an and statement.
I,
So we're going to look at some examples and see if it's true that every time we find an m times an n that's a perfect square, does it follow that both m is a perfect square and n is a perfect square? I mean, that's what we're trying to figure out, right?
right. Um, so we already know, like, if I were to view the statement, at first I was like viewing like the the converse of the statement being that if M is a perfect square and N is a perfect square, because the converse can be true.
But
And I
yeah,
like,
the converse definitely is true.
because I tested it out,
Yeah,
and we got 4 and 9, and for my homework I will pick different numbers. I tested another number, like another set of numbers, and it turns out that the statement is actually true if you pick if M and N are perfect squares.
that's true. It is true. The converse is actually always true. If M is a perfect square and N is a perfect square, their product will definitely always be a perfect square. You could
True.
prove that, but that's not what this statement says. This statement says if the product M times N is a perfect square, then M is a perfect square and N is a perfect square. We're trying to figure out if this statement is true, not the converse. But you're right, the converse is actually true.
But in this case, it's not always true,
That's
the
right.
original statement, because you can have two products to become a perfect square. Let's do 2 times 8.
Exactly. If M is 2 and N is 8, then M times N is 2 times 8, and that's 16, and that is a perfect square. But look at N and N, they're not perfect squares, are they?
Nope.
So that would be a perfect counterexample. You have just figured out that the statement is false.
And do I have to like write the negation for
It
that?
might be helpful. You don't have to, but it's always, if you're disproving something, it can be helpful to write the negation. And I think the instructions I give is if the statement is false, give a counterexample, write the negation carefully. I think it is a good idea to practice writing the negation. Like we can change this from words, I mean, we can use some symbols, but the point is, it's a for all statement because it's an if then, right? The original,
Actually, the negation would be like, instead of for all, the
right?
negation would be like there is at least one of M, so like a backwards E.
Yes. Yeah, there's at least one M and one N in the integers. Because I mean, the unwritten thing, what's implicit here is that M and N are integers.
True.
Because that's what it said. It said for all M and N in Z. That's what it actually says,
Yeah,
right?
but to negate it is actually there's at least one M and N
Uh-huh.
such that MN is not a perfect square.
Oh, let's wait a second. Let's be careful. This is an if P is
Oh,
then Q.
crap. Okay. Okay, M and are perfect squares, and M is not a perfect square, and N is not a perfect square. I just remembered in class.
Right. It's P and not Q.
Oh, okay.
So MN is a perfect square. And that's what you found. You found an MN that is a perfect square. It turns out to be 16. And, right, not Q. So how do we negate this Q?
M is not a perfect square, or N
There you
is not a,
go. Nicely done. M is not a perfect square or N or both because we use the inclusive or. So what you've got is fine. It's not the XOR, it's not the exclusive or, it's the inclusive or that we use. So
oh,
it's
okay.
okay if they're both not perfect squares because if M isn't a perfect square and N isn't a perfect square, then the statement M is not a perfect square or N is not a perfect square is true.
Yeah.
So this will work out fine for your counterexample.
Okay.
So, when you start your counter example, you're going to just say, hey, I'm giving a counter example. And you can just tell your reader to consider your values that you picked. Nice job at that. M is 2 and N is 8. And then you go through and you explain why MN is a perfect square and why M is not or N is not.
Okay. All right. Have a good night.
Oh, you're welcome. Good
All
night.
right.